and logical tradition of AI, and he has touched upon all these themes personally in his research, including in probabilistic programming, which I just touched upon. He introduced with collaborators here at Berkeley the log language, and has done some very interesting applications on it, and so I'm looking forward to his talk. So thank you very much for starting us off, Stuart.
Thank you, Dan. Okay, so I'd like to begin by thanking all of the students and collaborators who worked on this, particularly Brian Milch, and his PhD thesis was the basis for a lot of what I'm going to talk about. So I'm going to give a perspective from the point of view of the AI community of how logic and probability came together. Peter Cheeseman in the audience knows a lot about these things, having been one of the protagonists. There's, of course, other histories in the logic community itself, in philosophy. So AI got going in the 50s, and they looked at the real world, and they said, OK, we need to build intelligent systems for this real world. What do we know about the real world? Well, one thing we know about the real world, it has things in it. That's a very important observation about the real world. It doesn't have to be that way. We could live in a very much sort of a continuous fluid with no distinguishable objects whatsoever, but we don't. There are things in our world, and it's very helpful to think about them. And that naturally leads you to first-order logic, which is sort of the mathematics of things and relations among things. And this was the first proposed formal basis for AI in the hands of McCarthy and others in the late 50s. And so there were some very good reasons for doing this. It wasn't that this was the only possible choice. They really had no clue about how to do AI. There were people coming from information theory backgrounds, statistics backgrounds, linguistics backgrounds. Some people thought grammars would be the basis for AI. Some people thought that linear regression and mixtures of Gaussians would be the basis for AI. But logic provides a declarative substrate, so it means that you can express knowledge independent of its procedural use, and then find ways to combine it for all kinds of new tasks. You can learn it from all kinds of sources, from observation and communication. And first-order logic is sufficiently expressive to support pretty much everything that we need for general-purpose intelligence. At least that was the view at that time. And expressiveness allows for conciseness, and this is absolutely essential if we're going to learn our knowledge from experience. So let me just give you an example, the rules of chess, which is a very, very, very tiny part of the real world, and very, very simple compared to a lot of real-world theories. And there's only 32 objects and 64 locations and about 100 time steps. And if you try to write that using automata, it comes out to this many, about 10 to the 38 pages to write down the rules of chess. And you're basically describing the entire state of the chessboard as a single atomic object. And then you're writing a transition matrix among these. If you want to use something much more sophisticated, register machines or circuit representations, in propositional logic it's about 100,000 pages. And you have proposition symbols like the white king is on square c4 at move 12, all one word, right, with no internal structure. Okay, and then you have to write definitions of checkmate in terms of these proposition symbols. That's extremely difficult. And in first-order logic, it's about a page, about as long as it takes to write the rules in English. And in particular, you get to separate predicates and arguments. You get to quantify over those arguments and so on. And this gives you the expressive power that you need to do lots of real-world stuff. So, good. And this kept going until around 1980. And people did build real robots running using first-order logic theorem provers or specialized versions of that. But they found an obvious problem. They found this with robots. They found this with medical diagnosis, that they don't have the knowledge required to reach any conclusions whatsoever in most real-world situations. And that's because of uncertainty. So there's uncertainty in your state. You don't know what state of the world you're in because you have partial access to the state with noisy sensors. There's uncertainty about the physics of the world, so you can't predict with any certainty that a plan will succeed and so on. So we have what's sometimes called modern AI, where the canonical tool has been, until deep learning took over, probabilistic graphical models. So I'm going to give you, for those of you who are not familiar with those, a quick background on a particular flavor of probabilistic graphical models called Bayesian networks. So a Bayesian network is a way of defining probability distributions, and the sample space for Bayesian networks is exactly the same as that for propositional logic. So if I have 3 Boolean variables, has there been a burglary in my house? Has there been an earthquake? And is the alarm ringing in my house? Right, those are 3 Boolean variables, and they relate to each other in a certain way. Either of those 2 things can cause my alarm to sound. Then I can write a distribution, and the topology of the network expresses conditional independence relationships that hold, and those conditional independence relationships imply that the joint distribution over all possible worlds is written as a product of conditional distributions. So the probability of the burglary, earthquake, and alarm variables taking on particular values is the product of the probability of burglary happening, the probability of earthquake happening, and then the probability of alarm given burglary and earthquake. So if I put some numbers in, so 0.003 of a probability of a burglary, 0.002 of an earthquake, and then in the conditional table, for example, a 0.9 probability that my alarm sounds if there is a burglary and an earthquake, then the joint probability can be calculated looking like that. And you'll see that this is, the possible worlds here are just exactly the possible worlds of the propositional theory. Okay, so Bayesian networks are a propositional language. And in that sense, they don't have things in it. Right? There is no things for the Bayesian network to refer to or quantify over. So they don't work that well in the real world in terms of expressive power, although they handle uncertainty. Okay, so back to the history. What do you think happened next? Well, the first-order logic people realized that the world is uncertain, and the probabilistic graphical models people realized that the world has things in it. And that leads you to some kind of combination. And there's this phrase, which I'll explain in a second, a new dawn for AI, where we put first-order logic and probability theory together to get languages that handle uncertainty and have sufficient expressive power to do AI. And there was so that phrase actually comes from this story. There was a cover of A New Scientist, the Intelligence Revolution, and the story itself is I, Algorithm, A New Dawn for AI. And it says, at last, something else that thinks like us. Okay, that's complete rubbish, so I'm going to cross that out. But the point was that perhaps you might be able to get something that looks like human cognition because it has the symbolic capabilities of first-order logic and the ability to handle uncertainty, learn from data, to connect up to all the work in statistics and so on. So this idea actually goes back much earlier than 2011. In the early 90s, people like Jack Brees developed simple ways to combine first-order expressive power with Bayesian networks. And essentially, you just you put in logical variables and function symbols, and you allow quantification over those logical variables. So this says not, is there a burglary in my house? Is there an alarm in my house? But for every house, this is the structure of the dependency relationships among the variables. So house here can be viewed as a universally quantified logical variable. Region here would be a function symbol. So is there an earthquake in the region of the house, and so on. So you could then take this, which you can think of as a template, and you can combine it with facts about which houses there are and which regions each of those houses is in. So here's 2 regions A and B with houses 1 and 2 in region A, houses 3, 4, 5 in region B. So you basically take that set of facts with this relational template, and you combine those, and you can then produce a ground Bayesian network of the traditional kind, which in fact, in this case, splits into two independent networks, one for each region. And then you can do inference in the usual way, so you can supply evidence, so some alarms going off in house 1. The alarm is green, so that's house 2, 3, and 4, and not in 1 and 5. And because both alarms and earthquakes are quite rare, but the earthquake variable couples all the houses in a given region, the fact that there are 2 alarms in region B actually will give you an explanation saying that the earthquake is much more likely than a burglary in region B. And so, in some sense, you've built an earthquake detector just by that simple 3-line program. Okay, so that's good. So we could have saved ourselves a lot of grief by just realizing that the world is uncertain and it has things in it back in 1958. And we could probably have figured out something like this. However, that's not the only thing that happens. In fact, there's an interaction between uncertainty and things, which is that you don't know what they are. And so the language that I just described doesn't allow for uncertainty over what things there are, but in fact that's inevitable when you look at real-world applications. So, for example, if you're an insurance company, you may not know what earthquake regions there are. Right? You know what houses there are, but you don't know where the earthquake regions are. You don't know how they couple the houses together. Okay, if you're looking at citation data, you don't know initially what papers exist. You just have a whole bunch of citations. You don't know what authors exist. You don't know which venues exist. If you're doing natural language understanding, before you open the book, do you know who the characters are? Do you know all the locations? No. Before you open your eyes, do you know what objects you're going to see? No. So uncertainty about the existence of objects and about the identity of objects is central to almost all real-world applications that require first-order expressive power. So one way of thinking about what's going on is that the languages that we looked at, where you take Bayes nets and you combine it with logical variables and quantifiers and function symbols, was only taking advantage of part of first-order logic. And we might call these closed universe languages because they assume effectively the unique names assumption and domain closure. So unique names means that every object in the model structure has a unique term that refers to it in the syntax, in the language. Domain closure means there are no objects in the world, in the model structures, except for those that are named by terms in the language. Okay. And this is the core semantics for logic programming, for database systems, sometimes called Herbrand semantics. And many languages were developed building on top of logic programming, on top of description logics, and so on, that effectively had this closed universe semantics. So open universe semantics gets rid of unique names and domain closure, and that is the standard semantics for first-order logic. So the blog language we started in 2000, well, we started actually around 2001, but the blog language itself was published in 2005. And the whole tradition of probabilistic programming languages, which got going with a paper from Koller, McAllister, and Pfeffer in '97, and then Pfeffer's eyeball language in 2001, and is now a whole community to itself, takes on some of the same ideas, and I will explain the differences between blog and the typical probabilistic programming language later on. But let me give you a little test just to make sure you've understood this distinction between closed and open universe. So if I say that Bill is the father of William, and Bill is the father of Junior, and then I ask, how many children does Bill have?
2. At least one.
2, at least 1, at least 1, yeah. So it depends who you ask, right? If you ask Dan, who's obviously a closed universe kind of guy, he says, yeah, so in closed universe semantics, the answer is 2. So this is what a typical database system would tell you. If you say count, the number of children bear little, say 2. If you ask first order logic, the answer is somewhere between 1 and infinity, right? Because obviously William and Junior could be the same person. There could be other children that we didn't mention. And my point is that for a lot of real world applications, we need the second kind of semantics because of this uncertainty about what exists. So in pictures, the possible worlds look like this. So if you have closed universe semantics, and we say that there are 2 symbols in the language, A and B, and 1 relation, then there are exactly 16 possible worlds, and they all have A and B. So these are the worlds. This is up in syntax land. So they all have 2 objects, A and B, that are distinct. And the symbol A always refers to A, and symbol B always refers to B. And the only thing that changes is the relation. So here, the relation is empty. Here, A is related to itself. Here, B is related to itself. Here, A is related to B. And here, everything's related to everything. Okay. So it's nice. This is homogeneous. It's often finite. And it's relatively easy to specify distributions over this set of possible worlds. This is the open universe case. So A and B can refer to the same object, or they can refer to distinct objects. There can be lots of objects that aren't named by A or B. And so you have an unbounded set of worlds, and it's much more heterogeneous. And so the question is, how do you get to define probabilities on this more complicated set of possible worlds? So that's the task. And the idea for how to do that actually comes from a way of thinking about Bayesian networks as little machines that construct possible worlds. Okay, so if I take this Bayesian network and I just simulate it, so I pick a value for burglary, let's say, comes out to be true. I pick a value for earthquake, comes out to be false. Pick a value for alarm, it comes out to be true. I've constructed a possible world just by simulating this as a little stochastic machine. Okay, so if I want to make worlds with varying numbers of objects, then it seems like what I need is a stochastic machine that can not only set the values of variables, but can actually add objects to the world. Okay, and so some of the steps when you simulate the machine, the stochastic machine that's represented by the program, will be steps that add objects to the world. So that's the basic concept. It's really quite simple. So we have 2 kinds of steps. We have the regular steps, which set the values of variables. You have a question?
So I'm not sure I understand. Well, I understand the difference between closed and open universe, but it seems like closed universe is just marginal distributions of what we have in the open universe. I mean, just we kind of ignore the variables that we don't know about. But just is the probability 1% or 1/100% that the alarm will go on even if there's no earthquake and nothing we know about? Why? Because there are some other reasons.
Okay, so in the open universe version, right, there will be, for example, we are getting alarm signals, but we're not sure which houses they're coming from. We're not sure how many houses there are, and we don't know what geological regions exist. Okay, so if you marginalized out all that uncertainty, you would end up with a giant mess. You would have to have a lot of indicator variables, and everything would be completely connected. So, yeah, so it's important to, if you want to have a concise representation of the domain, right? It's important. Effectively, what you're doing is you're marginalizing out all the objects, right?
Everything rest. I don't know what it is, but it's everything else. And I kind of write condition on everything else.
You mean you marginalize out everything else? Right, but if you marginalize out the objects about whose existence you're uncertain, then you're down to a propositional language. And a propositional language where everything is completely connected, and so you have no conditional independence, and you can't even write down what the model should be. So we can talk more, but if you go through an example, you'll see that. Okay. All right, so in the language, we have, just as with the quantified Bayes nets, we have ways of writing these quantified dependencies among variables. So again, think of H as being universally quantified. So for every house, whether or not the alarm sounds in a house depends according to some conditional probability table on whether there's a burglary in the house and whether there's an earthquake in the geological region of the house. Okay, so that part covers the closed universe languages. And then in order to have a mechanism for adding objects to the world, then we have what are called number statements. So here we'll say that in some sense the geological regions are just exist, and there's somewhere between 1 and 10 of them. And then the houses exist in regions. So the number of houses in a given region is, let's say, Poisson with a mean of 50. And I just want to give you a little piece of terminology that this function here, region, the region of a house, we'll call it the origin function, because in some sense we think of this as how the house comes into being. It comes into being because there's a region in which the houses get put. Okay, so the semantics of the language can be built up in a fairly standard way. The key difference that we'll see is that the objects in the model structures are not just tokens, they're not atoms, but they are descriptions of the generation history of that object. Okay, and that turns out to be quite important. So, and it's a type logic, so everything has a type. So we have an object in the model structure called a geological fault region. They have no origin, they're sui generis, if you like. So the origin is blank, and this is the third geological fault region. Then we have houses, so we have a house whose region is geological fault region number 3, and it's the 97th house in that region. Okay, so those are the objects in the model structures. They are essentially generation histories. And then a random variable is constructed by taking one of the predicate or function symbols. In this case, is there an earthquake? And then essentially, for every possible tuple of arguments of the right type, so for all of the objects we have in the model structure, we construct a random variable by subscripting the tuple of objects to the function symbol or predicate symbol. And then in any given possible world omega, this has a value true or false. Okay, and then to build up the whole possible world, right? We just imagine sort of simulating the program in the forward direction. We generate numbers of objects from the number statements that populates the world with the objects as we go along, and then we construct all the random worlds, all the random variables from all of those objects. And then we give values to all those random variables, and then the world is complete.
I mean, imagine the CPT is fixed, the same CPT is being used for
so you can have fixed CPTs, or the CPT entries can also be random variables, so you can do hierarchical Bayesian models and all the usual stuff. Okay. And then, so that's a possible world, and then the probability of a world is, just as in Bayes nets, the product of all the conditional probabilities for generating each piece of that world as you go along. Okay, and so this is why we have this slightly Byzantine construction of the objects themselves, why they're not the usual featureless tokens of first-order logic model structures. And we need that because we want there to be only one way, one path through the program that could generate that particular possible world. So if you had featureless objects and you had a particular world with particular relations holding among particular objects, there could be combinatorially many paths through the program by which that particular world can be constructed. And then even to write down what the probability of that world is would involve a difficult combinatorial exercise in general, particularly if you have recursive functions. Whereas here, it's completely straightforward. Yeah?
I have a clarification question. when you say a possible world, does this include just the objects or also the values of the indicator variables?
The values of the indicator variables.
So there are no more probabilities left once you have specified.
Yeah, so with a possible world, the answer to every question is fixed. Yeah. Yeah, so it has the same properties as typical model structure and logic. Right, so I said that. Good. So then it turns out that if you make certain restrictions on the model that you write down, for example, you don't want to have infinite backward chains because then there's no root variable, as it were, for the network. And you don't want to have cycles, so you can't have variables that strictly depend on themselves. You need the expression, so the language includes arbitrary logical expressions in the conditional sentences, so you can have if and then some logical expression. If that logical expression can't be finitely evaluated, then you're stuck. So you can't say, if Fermat's last theorem is true, then there's the burglary with probability 0.8, right? Because
Wait. You have to update your example because we know it's true, right?
Yeah, but the inference engine won't know it's true, and it would be very hard to write the semantics in such a way that that was true. It was guaranteed. So just as with Turing machines, right? There are going to be blog programs that do in fact define a proper probability distribution over all possible worlds, but we won't be able to tell whether they do or not. But there's a subset of the language for which we can tell, and this is a subset. There are other bigger subsets that would need more work, but these are sufficient conditions for the probability distribution to be well defined. And these are conditions that we can check. Okay, so I'm going to give you some examples, and then we'll talk a little bit about inference. Okay, so here's a nice simple one. There's a test, another test. It's a very difficult morning for you. I know it's early. So here are two citations. And the question is, are these citations of the same paper? Okay, who thinks yes? Yes. Who thinks no? Okay, and who is uncertain? Everybody else, right? Most people are pretty uncertain. So yeah, it varies. Sometimes between 10 and 90% of people say yes, depending on the audience. If this was a mostly AI audience, you'd probably recognize that the National Conference on AI is the same as what we usually call AAAI. And so this is probably the same venue that Cambridge is the location of MIT Press, whereas Seattle is the location of the conference. If you know about BibTeX, then you can see that probably it's the same author list, except they put a comma in the BibTeX author list, which then screws up how the authors appear when you generate the LaTeX from the BibTeX. And so you'd say, yeah, this is almost certainly the same thing. And you also know that Potimas is not likely to be publishing multiple papers with the same title. And on the whole, you'd think, yeah, this is the same paper. Right? But it's clear this is uncertain, and this is absolutely typical. These are relatively benign examples. There are much worse citation strings than this. And this is what Google Scholar and CiteSeer and all of those engines have to deal with when they construct the citation databases that we just take for granted these days. Okay. So, but this is the core of what those engines are doing, is deciding for any given pair of citations, is this the same paper, right? Because without that, you can't even begin to build the graph of citations. So we're going to take all this data, millions and millions of these, and we have to decide, okay, what papers exist, what researchers exist, what authors, and for each paper, what is its real title, what are the real authors, and what is the citation graph. Okay, and so I actually started working on this problem because when CiteSeer came out, like everyone else, I typed in my name. Like I typed in Russell and Norvig, and which is there's the two authors of a textbook. And so CiteSeer said that we'd written 120 books. So CiteSeer was clearly failing at at doing this citation matching problem, right? It had over-segmented. There were about, at that time, 1,200 citations of the book, and it had segmented them into 120 different books. So there was obviously a problem to be solved. And imagine doing that with terrorists, right? So you're wrong by a factor of 100 on the number of terrorists in the United States. That either way would be bad. Okay, so this is a slightly simplified model for publications with a single author, and I've left out part of this, which is the model for the grammar of citations. But this is the core of how the model is written. Right? So we start by saying, okay, what exists? Well, there are researchers and there are papers. We don't know how many researchers. We don't know how many papers. And we found that log normal is a nice, so it's actually a discrete form of a log normal distribution. It's a nice way of describing numbers about which we are very uncertain. And this basically says, if I remember correctly, it's 100,000 plus or minus a factor of 10. So it's you get a multiplicative standard deviation, if you like, because of log normal. And then the number of papers with a given author, so here the papers are seen as having the author as the origin function. Right? So the number of papers by a given author, if it's a professor, then it's 100 plus or minus a factor of 10. Otherwise, I think this is 10 plus or minus a factor of root 10 or something like that. So that describes what we might expect to see in the domain. And then researchers have names, and we have basically a prior over strings, which is drawn from the US Census database. And papers have titles, and we have a word trigram combined with a letter trigram prior, which is derived from a whole database of millions of computer science papers. And then the meat of the model, so this sort of basically sets it up. This is the declarative part, what the COBOL people call, I think, the data division. And then we have the stuff about citation. So C refers to a citation. So the publication cited, we'll assume that when you write a citation, you're just choosing a paper at random to cite. Okay, so it's a very weak model of how people choose what to cite, just uniform from a set of papers. Okay, now you could obviously add in, something about, we could add prominence for papers, and again, you wouldn't know a priori how prominent any given paper was, but you just say, well, its prominence is between 0 and 1, and that then goes as a weight into your choice of which paper to cite, and maybe prominence in a particular field or relevance to the topic of the paper that you're writing. So you can make these models more and more sophisticated, and they will perform more and more accurately. But usually, in a typical Bayesian way, even if you have very weak priors, the data will sort out a lot of this stuff, and you don't have to be very precise with the priors. And then there's the text of the citation string itself. So basically, the citation string, again, this is a simplified version of the true model. The citation string is built from the name of the author of the cited publication in this citation and the title of the cited publication, neither of which we know, right? We don't know who the author is. We don't know what his name is. We don't know what the title is. But whatever they are, the citation string is built from those. Take that information, shove it through some kind of noisy grammar for citations, which includes the ability to introduce spelling mistakes and punctuation errors, and all the things that you actually see in citations. And again, it's not a very specific grammar. This is actually an HMM grammar, so it's much weaker than the grammars that you could build if you took all the BibTeX citation types and built grammars for those and so on. Okay, so that's it. Right, this is a citation matching system, and so you write that model, you supply the data, a bunch of citation strings. You then ask a query, right? So you have a full logical query language. You can ask anything you want, right? Okay, how many papers are written by 3 authors, all of whose name is Blum, right? You can ask that. There are some, actually, by Manny Blum, Lenore Blum, and Avram Blum. You can ask basically anything you could express in a logical or SQL-like language. But these are the basic things you want. What papers exist, who wrote them, what's the citation graph. Okay, and if you then put this into the completely generic inference engine, here's the problem, right? You have to wait a long time because completely generic inference engines don't know about how to parse probabilistic context-free grammars efficiently, right? They don't necessarily have the ability to invent dynamic programming algorithms on the fly. There are all kinds of things that they're not going to invent that are the subject of algorithm design for the last 50 years. So a generic inference engine in general will be slow for most of these. And as we'll see, to get it to work faster, you have to develop efficient proposal distributions for the MCMC inference. Okay, so we compared this. This is data from quite a long time ago when Sightseer was the best citation database out there. And Sightseer provided some test data sets for comparison. And here the metric, this is an error metric, which is the percentage of papers for which there is any error. So any error means that you are missing one of the citations for that paper, or you've added in an extra citation for that paper that in fact is not referring to that paper. Okay? So it's the strictest possible error for citation matching. And you get these error rates with Sightseer, and with the blog model that I just showed you, just the only real change to it was to make it allow for multiple authors. We cut the error rate by a factor of 2 or 3, and later on, with a more sophisticated model, we got it down to about 1%, so which is comparable to where humans are, because there are a lot of citations that are just deficient. They contain, for example, only an author name or only a title, and you can't really figure out what's going on. Okay, so we built now quite a large library of example programs in blog. So some typical machine learning ones, PCFGs, a Ball-Known model, which is like species counting, so finding the number of distinct objects by repeated draws from a set. Topic models are easy to write. All of these are all 5 or 6 lines of blog. Auto-regression, Kalman filters, infinite state HMMs, and so on. There are some slightly more complex models. So Sybil attack for cybersecurity, that's people who use multiple logins to attack systems like TripAdvisor or eBay by generating fraudulent recommendations and transactions. Multi-target tracking, so let me just show you the multi-target tracking model. So the multi-target tracking and data association is what you do when you have radar and they generate blips, and then as the radar goes around, you get more blips, and you have to somehow connect up the blips to each other and form tracks. And this is a whole sub-area with thousands of journal papers in the electrical engineering community. And in some sense, this is the sum total of all that work. Right? And the nice thing is that, so this is a standard model. So aircraft arrive at random. So the number of aircraft you'll see is a Poisson. They can leave the region at any time. They stay in flight. They stay within the visible region with a certain probability. So X is the state of each aircraft. Z is the observation value for a blip. And so this allows for aircraft appearing and disappearing. It allows for detection failures. It allows for false detections of non-existent aircraft. So this is a quite sophisticated model by the standards of the multi-target tracking community. But if I want to, for example, allow aircraft to follow each other as opposed to follow independent tracks, which is the standard, right? I can do that by changing 1 or 2 lines of the program. If I want the aircraft to take off and land from unknown air bases, I can add that in. So aircraft actually now have a destination and they go somewhere instead of moving randomly. I can add that in. So you can do elaborations which would be whole PhD theses worth of work in the traditional way of doing things. You do a whole bunch of math, you write a whole bunch, 10,000 lines of C++ code, and you can do that in 1 or 2 lines of modification to the blog. So we actually even done some vision, and we've actually gone through this exercise with online video background subtraction. So this is how you find and track moving objects in video images. And we've shown that indeed, you can write 2 or 3 lines of blog to make the model more sophisticated and take into account additional factors about the tracking problem. We have an extension for, yes?
This is something very basic I don't understand here. What's the nature of the answer your system is giving? Is it a sampling answer? Is it an approximation?
It's a posterior distribution. Depending on the algorithm, if we're usually using MCMC, so it's an approximation to the posterior obtained by sampling, yeah.
And how does that connect to the first segment of your talk, which was about open models as opposed to closed ones? Are those models open?
Yeah. So in the multi-target tracking, for example, if it's a very noisy radar, then it would say there may be 3 or there may be 4 aircraft. If there are 3, these are the tracks. If there are 4, then those are the tracks, and that's where the other one is.
But in the citation example, you were reading off in your code something from an actual database. Is that right?
No. So the evidence supplied to the model just consists of citation strings. Okay, so literally ASCII strings. Okay, and then the query is what papers exist. And we'll say, okay, there's a paper, we'll call it P1, it has these 12 citations, it has this author, and so on. So you can ask relative to the most likely world, or you can ask marginals against the posterior distribution, and so on. So there's different kinds of query interfaces. But think of it as you put in ASCII strings, and it gives you a posterior over citation databases. And against that posterior, you can ask any query that you want. All right, so I just want to mention that there's a decision extension which allow you to specify actions and utilities, and then an engine that can evaluate and modify policies. So one example is playing invisible opponent monopoly. So you're playing Monopoly where you don't know where your opponent's piece is and you don't know which properties he's bought. The only information you get is that every so often you receive money or you have to pay money, and you have to figure out what's going on from there, and then have a policy for whether or not to buy a given property. You have to guess whether your opponent has any of the other properties in the set based on all the evidence that you've seen so far. So that's a fun. It's surprisingly capable of playing that fairly well. Okay, so inference. So for all of those models that we can detect are provably well-formed blog models, the inference algorithms that we've developed are complete under the usual caveats about MCMC and other sampling algorithms being complete, that everything has to be ergodic and so on. So, so I think that there are clearly huge amounts of work to be done on inference, particularly for handling the fact that in many models there are deterministic submodels which will mess up MCMC algorithms. And we are working on some of those. But let me just mention some advantages of using MCMC for this kind of problem. So the MCMC is wandering around in the space of partial model structures. Okay, partial because the model structures are unbounded size. For example, we may have no limit on the number of houses in a region. In fact, the Poisson doesn't have a limit on the number of houses in the region. So there are model structures of arbitrary size. But if we don't have any evidence about those houses, we don't have to instantiate them in the model structures. Okay, so we can work with partial model structures, and effectively we're then integrating out all the stuff about which we have no information, and that's easy to integrate out because it's all the same. So we're wandering around in the space of these partial model structures. This has many advantages. So it does not require that any work be done to calculate by the user to do any of the math required to calculate any of the transition probabilities. So once you've written out your blog model, the blog engine essentially does all the math to calculate transition probabilities appropriately. Because it's a sampling algorithm that's just generating has one sample state at a time, the space requirement is trivial. The main calculation in MCMC is to calculate this acceptance ratio. This is the probability of the new state x primed. This is the probability of the old state x. These are the proposal distributions in both directions. And because the probabilities of the worlds are products of probabilities for all of the instantiations of the random variables, and you're only changing one or a small number of random variables at a time, almost all those probabilities cancel out. So your calculation of this transition ratio is entirely local and usually trivial to carry out. And also you can incrementalize the calculation of the query. So you have to evaluate the query on each state, but this is a well-known technique in database systems that you can incrementalize that. So as you change the state by changing the values of some of the random variables, you can recalculate the value of the query without running the whole query over the whole world each time. So we can make things quite efficient.
Small question.
Yeah.
How do you decide what kind of steps you can take locally? So you're like in one of your partial worlds, X, and then you have to move to X prime. So there's a number of X primes.
Yeah. So you pick essentially you can pick a random variable which could be one of the variables saying whether or not a relation holds between some objects, and you can change its truth value, or you can change the number variable. So you can create or destroy one of the objects.
So you can grow your world,
yep,
add the new region, or regret and delete one.
Yep. Yep.
So it's the syntax of your program that's going to decide what are the moves you can take.
Yeah, exactly. Yeah. And it's usually those other the moves that create and delete objects are the ones that usually cause the MCMC to run slowly, because. For example, if you have a region that's nicely sitting there with 53 houses and you delete that region, then all the houses have got to pick a new region, and they're probably not going to pick a good one, and then you're going to have a very bad world, which is unlikely to be accepted by the MCMC. So generically, those birth, death, or split merge moves are the ones that cause you problems. Okay, in the interest of time, I'm going to skip over the relationship to probabilistic programming because I think a lot of people are going to talk about this during the week. I'm just going to mention briefly some work that we've been doing recently on inference. So for the programming language people in the room, this might be completely obvious, but pretty much every description of a probabilistic inference algorithm, whether it's on Bayes nets or the closed universe probability models or the open universe probability models, describes the model as a data structure. Right? The Bayes net is a data structure. And then the algorithm operates on that data structure to do inference. Right? This is effectively being an interpreter for that program. So think of the Bayes net as a program, then operating on that Bayes net as a structure is running an interpreter on that program. And you get all of the overhead that you get for interpreting Prolog or interpreting Lisp or interpreting any other programming language. So what you should be doing instead is taking the model and then generating the inference code for that model specifically, because the model itself is not going to change while inference is running. Okay. That gives us a very large speed. So our original blog engine was doing that. It created an internal data structure representation of the model, but it was still a data structure. When instead we just generated code directly, which then is running inference specifically for that model, we got the typical 2 orders of the magnitude speed up. We compared it with Bugs, which is probably the most widely used Bayes net package, and on the same model for the same algorithm, it runs between 700 and 1,000 times faster. Okay, so we're getting way more expressive power than Bugs, because that's strictly a Bayes net language with the ability to, so it's a closed universe Bayes net language. We have way more expressive power and 3 orders of magnitude more speed. So we can run, for example, on a laptop at about 100 million samples a second. And we're spending most of the CPU time inside the random number generator. So the inference overhead is pretty small. And then there are lots of other things we can do, which I'm not going to go into. And there's a graph showing the various speedups. And so the compiled blog is down here, and then these are the other various systems that people have put out there. I want to talk about an application to nuclear monitoring. So this is a map of the various locations where nuclear testing has been done. And this is North Korea, which is, so every time I give this talk, I have to add another one to the number of explosions because North Korea keeps doing it. There is theoretically a ban, which has not yet gone into force. Just to give you a little visual sense of what a nuclear test looks like. This is the crater from a very small nuclear test. This test was 1/500th of the size of the largest test that was ever done. They make quite a big bang. So the treaty was proposed in '58 banning nuclear testing. And it was signed, it was open for signature in the UN in '96. Almost all countries in the world have signed it. It's a very tough treaty because if there's evidence that you have been testing, you essentially agree to allow yourself to be invaded, and 1,000 square kilometers can be occupied and inspected. Unfortunately, the US hasn't ratified it, so that means the treaty hasn't gone into force. But the US is at least honoring the treaty. And the UN has built a network with 278 monitoring stations around the world. Seismic is the most useful evidence. We don't expect people to be doing air testing. It's all underground. So seismic is the main source of evidence for testing occurring. So you are familiar with what a seismogram looks like. This is a magnitude 6 earthquake. So on this scale, a nuclear test might look like that little bump over there. And so it's not easy to find nuclear tests, particularly because there's a massive amount of background noise. So the goal of the monitoring system is we have all these monitoring stations collecting data in real time. What we need is to output a daily bulletin, as it turns out. These are all the events that took place of any reasonable magnitude. Okay, I'm running late. Where did they take place? How deep were they? How large were they? And then usually the nuclear explosions will be fairly easy to sort out from that list. And it's a hard problem because there's a massive amount of noise. And so the UN has spent a lot of money, over $1 billion, building this detection monitoring network and all the software. And yet they're only able to detect about 69% of the events that they would be interested in. And then they have a whole bunch of human experts who are then sifting over what's left and trying to figure out all the other events. And the whole system, including the humans, is still not very good for low magnitude events. As I said, there's a lot of background noise. The geophysics of the world is quite complicated because every event produces dozens of wave types with different velocities, and it takes hours for those wave types to propagate around the world. And so it's like having thousands of conversations all garbled and mixed together and then arriving at hundreds of different microphones. Okay, so here's how it works, right? There's a bunch of detection stations. An event takes place. Seismic signals propagate from the event. They reach the station. They cause blips. So here, 2 blips arrived at the station at the bottom, then another event, a blue one, and then some blue blips arrive at the top station. Notice that the blue and the red blips switched in time sequence because of different locations. And then at the end, you have a bunch of blips at a bunch of stations, and of course they're not colored, right? We don't know where those blips came from. And so we have uncertainty about what events exist and about which blips are associated with which events. So it's a typical open universe probabilistic inference problem. So we wrote a blog model. That's the blog model that I wrote. It describes all the geophysics that I just said. It allows for uncertainty in propagation time and detection and all the rest of it. Includes a model of noise. I'm going to skip over it. This is a picture of part of the prior for location of natural seismic events. This is the probability detection as a function of magnitude and distance from the event. This is the uncertainty about the travel time prediction. How long does it take to get to a given station from a given source? And so on. We ran it on a bunch of data, which the UN gave us for a 3-month period. This is the fraction of events missed. So in the existing UN system, between 30 and 50%, depending on magnitude, are missed. And the Bayesian model, the blog program, just running on the data supplied from the seismic stations, has about a 11 to 12% failure rate. So it's effectively about a 1 magnitude reduction in the sensitivity level of the system from exactly the same data. And this was a couple of years of one graduate student basically getting the inference to run fast enough to make it real time. Okay. So I think that the evidence shows that these kinds of languages can do very useful work and do it better than traditional software construction techniques. This is a little piece of data from a test 3 years ago in North Korea. So this is where we think the event took place from satellite photographs. That's the tunnel entrance to the underground testing. This is the best guess of the UN as well as the USGS and all of their human experts as from all the seismic data, and then this is the location estimate from our system as to where we think it is, with the uncertainty contours shown. Okay, so I think this system will be the new monitoring system for the treaty, according to the UN. And just to sum up, there's a lot of stuff, real work still to do. I think inference is the primary task here. I think from the point of view of representation power, for the applications we tried, it seems to work. You know, if you have enough of a clue about what is the causal structure of the domain that you're looking at, then you can express it pretty well with this language and with some of the other probabilistic programming languages that we looked at. And for all of these languages, making inference sufficiently fast to be practical. So for the seismic case, we spent a long time working on proposal distributions to make it mix quickly. And that was where most of the time went. Okay, and so one of the things we're looking at now in particular is natural language understanding. As I mentioned, with natural language understanding, you have the same problems. You don't know what objects you're going to be reading about. You don't know how they're going to be referred to. Are they going to be referred to as Mr. President or Mr. Obama or Barack Obama or the President or any? There are many, many ways you can refer to objects and events. We also allow for uncertainty about even what words mean or what relations exist. So you can have uncertainty over the relations that exist, and then the system can figure out from text what relations exist and how they're expressed in text. So you can do completely unsupervised natural language understanding using these techniques. Okay, thank you very much.
Time for a question or two.
I see that you have French funders. So
Yes.
who are these people you're working with?
So I was on sabbatical in Paris for 2 years. So I had an ANR Chaire d'Excellence, and then Ile-de-France funds the Chaire Blaise Pascal.
So I have a more scientific question. So, so you have this generic syntax, and it's very expressive. And then for each, I say no if I'm wrong, right? What I understand is that for each specific model you're building, you're going to design a new strategy to infer. And then it's incredibly more efficient than generic strategies. Is that right?
Yeah, so some applications, so we did one, the video background subtraction. So we have a generic inference algorithm for temporal models, which does a kind of particle filtering. That's another, like MCMC, completely generic. And that's now, with the compiler, fast enough to do real-time video processing. And we didn't have to write any special proposal distribution for that. So on some applications, the generic stuff is now fast enough. But on others, yeah, particularly, as I said, where you need to do split merge or birth-def proposals to figure out what objects exist.
I don't understand. How can you be so much more efficient than people who are solving specific problems, even though they don't have the same level of generic expressivity? It's just like, this is something intuitive that I don't understand here.
So you're talking about the comparison with bugs?
So you just said that in a particular vision problem, you had a pretty generic strategy for compiling, and that you're better than people who are just doing this?
No, I just said it runs in real time. There are plenty of other vision algorithms that run in real time. You can